Okay, everyone. This is another lecture about your the DC to DC converters. In this class, we're going to discuss about buck converters. Buck refers to step-down conversion, and these are switch mode power supplies. Here, I have shown you a very simple example of a buck converter that typically you use for step-down conversion. You can buy it any electronic retail shop. So basically what it does is you have to feed any DC input supply to plus and minus battery voltage or any DC voltage here, and you can take the convert this voltage back to the step down and get this output from here. So this is a control or the IC of the power supply, which has this all the control circuits, and this is this inductor. You need to have an inductor for this switch mode power supplies, and you need to have some additional filter capacitors, the output capacitor and input capacitor, and this power diode. And there are some small feedback resistors and capacitors. Sometimes you can buy this control as an adjustable version, so which means like by changing this voltage, you can change the output voltage to any desired level. So these are based on inductors, and previously we have discussed switch capacitor converters, but in today's class we are using inductive based step down converters, also known as buck converters. So this lecture covers the comparison of three basic DC to DC converters, which we have already discussed two types earlier, and today we going to introduce this switch mode power supply. And secondly, the basic operation and characteristics of an asynchronous buck converter. I will explain you what is the asynchronous means in these converters. And we're going to discuss the power losses, and finally a practical design example using with a datasheet and simulation example. So why we need a switch mode power supply? So far we have learned linear regulators and charge pump converters. So still we can build any DC to DC converter using linear regulator or charge pump converter. Why we need a switch mode power supply? So that I explained from this table. Here we can see there are some additional advantage of switch mode power supplies, which are using the inductive switches. If let's take a look at the conversion type of these three topologies. These two we have already learned, and today we're going to discuss this one. And the voltage conversion type in a linear regulator, it is always a step down. You can't step up or invert this voltage. So linear regulators are only limited for step down voltage regulator. For example, you can convert any 12-volt battery supply to 5 volts for your Arduino, like that. And charge pump converters, they have these all three conversion types. It can step up, or it can step down, or either it can change the polarity. For example, last week we have discussed how to build a positive to negative voltage converter using a charge pump converter, right? So switch mode power supplies also offer all these three conversion types, and this output voltage regulation. So which means like the output voltage is fixed. So linear regulators always provide a fixed and regulated output voltage. Charge pumps, depending on their controller, sometimes it will generate an unregulated supply, or sometimes it will provide a fixed regulated supply. Unregulated simply means like if the input voltage changes, the output voltage also changes. Regulated simply refers to it is providing a fixed output supply, right? And the switch mode power supplies always provides regulated supply. That is very important. So operating frequency, linear regulators, they don't need to switch any controller. So it's like a transistor or MOSFET driven series pulse device. So no switching. It's pretty linear controller, and charge pumps, they are switched between this frequency range, 10 kilohertz to 1 megahertz. Switch modes are typically driven in 100 kilohertz up to 4 megahertz. So efficiency-wise, the linear regulators are the lowest efficiency type, and the charge pumps can increase the efficiency compared to a linear regulator, and the switch mode offers the highest efficiency. Theoretically, you can achieve 100% efficiency, but in practical scenarios, due to some losses, the efficiency is a little bit lower, typically in the range of always higher than 85%. So if you buy a very good controller, you can simply achieve around more than 95% efficiency. So linear regulators are complexity-wise very easy to implement. It is a very simple design. You have seen like it has only 3 pins. You just plug and play, right? So sometimes you just need to add some output capacitor, that's all. The charge pumps has a moderate complexity. It has some switching capacitors. You need to have some switches to switch the capacitor between the charging and discharging phases. And the switch mode power supply are the most complex one to deal with, right? So their complexity is moderate to high. So when you add those EMI filters and all these extra components, so the design complexity is always high. So the noise at the output voltage, the peak-to-peak ripple voltage, and EMI is electromagnetic interference. So that is radiated or conducted noise. So in linear regulators, the lowest noise and EMI, the switch capacity, because it is linear, no switching involved. The switch capacitor converters has moderate noise and EMI because it is also switching the capacitive pairs. The switch mode has the highest EMI because it is switching inductors. So inductors sometimes acting as antennas when you're switching at this kind of high frequency. So therefore it has high EMI. So depending on the output current deliverability, the charge pumps offer the lowest output current. The linear regulators can provide moderate output current. Switch mode power supplies has the highest output current capability. Output power also highest in the switch mode power supply. Dynamic response is something related to like a step load change. Like when you change your load from 0 to 100%. So like this is your load. So you have 0 milliamps and suddenly you change it to the maximum load, let's say 1 amp load current. So you just switch your load. So this tells the how this output changes, right? So you are expecting no matter how you change your load, so you're expecting, let's say like 5-volt output. But the time that you just switch on your load, so the output will be, it will go down and then settle there. And if you turn off the load, it will go up and go like that. So it's like this. This is your 5-volt reference, and this is your dynamic response, right? So if it is has a like a very this time should be very short, which means it should settle down to the 5-volt immediately, and these kind of peaks and bumps should be avoided. So if the linear regulators always provide the fast transient response. So no matter how if you've done the simulations I have asked you to do, so you can just compare their responses. So the switch mode are very slow, which means like when you switch this on, so it takes a lot of time to recover, and when you turn off the load, it takes some time to recover back to your desired voltage, right? Sometimes in most design in power electronics, you will end up with if you need more dynamic response, sometimes you can just you have this high efficiency buck converter, and you can add some linear regulator LDO just after the buck converter. Then you can get a very good dynamic response even the efficiency might be 1 or 2% lower than this using still the buck converter. But when you add the LDO regulator, you will just reduce the efficiency slightly, but you will get a nice and fast transient response with a very low output noise. So that is called as post regulation. It's a common thing in power electronics. Most of the power electronics engineers are using that technique. As this we are dealing with inductors in this switch mode buck converters, so I will demonstrate you the basics of inductor. So that will help me to explain you in detail the conceptual design of a buck converter. So let's take a look at this video first, then we can see how this buck converter works.
The purpose of an inductor is to oppose any change in the magnitude of current within a circuit. The electrical property that resists either an increase or decrease in current is known as inductance. An inductor is created when an electrical current flows in a wire wrapped around a magnetic core. You may recognize this as an electromagnet represented by flux lines that develop around the core with the formation of a north and south pole at their respective ends. To demonstrate the properties of an inductor, we'll add a resistance or light bulb to this circuit. As the switch is closed and the current flows through the circuit, the electromagnetic field in the inductor forms and expands rapidly. However, because of the unique properties of an inductor, as the flux lines of the electromagnetic field expands, the changing current generates a voltage that resists the current coming from the source. The maximum opposition to current flow occurs at the instant the switch is closed. Therefore, the bulb will not turn on instantaneously. However, once the electromagnetic field stops expanding based on the level of changing current, the flux will no longer generate an opposing voltage in the circuit. The current will continue to flow and reach its maximum value after 5 time constants, or 5t, where t is equal to L divided by R. The light bulb will then be at its maximum brightness. If you open the switch and stop the flow of current from the source, the electromagnetic field will diminish rapidly and simultaneously release stored energy in the form of voltage. It will actually generate enough voltage to cause a spark across the switch as it opens. Whereas a capacitor uses voltage to store energy, the inductor uses current.
Right, you may have seen how this works. So the thing is that, so when you just turn off an inductive circuit, like so the inductor was carrying some current like this. So if you just remove this connection, so the inductor current does not change instantaneously, which means it needs a path. So that's why this providing some arc in here. To avoid this concept, you have seen in most of the relay circuits, so we had this freewheeling diode across this one. So in normal scenarios, this diode is preventing the current flowing from here, but when you just turn off this switch, so the inductor current is now flowing in this direction, so it has all the freedom to circulating back here. So which means like it had this electromagnetic field across it. So while this circulating through this diode, so there is some power loss as heat, and there's resistance of these wires and everything. So the stored energy is dissipated, and these flux lines get disappear over the time, right? So otherwise, if there's no freewheeling diode, so there will be huge spark around this switch. And the other interesting thing is, like in the capacitor charging circuit, the capacitor voltage start from 0. But in the inductor circuits, when you switch on this one, so that the light bulb is off, right? Which means this the battery voltage VB directly go across the inductor, right? Because the inductor has highest impedance at the initially because it doesn't have any flux. So it gradually creating this flux, and this VB goes down. So once it is created, is all the flux lines, and it is saturated. So this inductor will just act as a piece of wire. So it's like a literally short circuiting between its terminals once this magnetic flux is created. So then this it's like this inductor is a piece of wire. So all the current now can flow through this light bulb. So piece of wire, the voltage is 0, and the battery voltage goes to the across this light bulb, right? So initially all the voltage goes to the inductor as its inductive field is created. So it's acting as a piece of wire. Then this the voltage is transferred back to the light bulb. So these are very basics of the inductor. So most of the people who is working in working sometimes forget this concept, and sometimes they forget what is freewheeling diodes and everything. So they will end up with destroying their circuits, right? So always remember to follow your fundamentals and basics. So that will help you to work without an issue. All right, so now we are moving to the real scenario, which is the asynchronous buck converter. So this is for step-down voltage conversion, and it requires a power switch. So this is a simple circuit diagram of a buck converter. So you have this power supply. It could be a battery, or you can add the input capacitor as well. And this is your power switch, which is this simply a switch, like in switch capacitor converters. Also, this is a power switch, right? So you can control this switch turn on and turn off using a gate pulse applied to this transistor or the MOSFET. And this is your inductor, and this is a freewheeling diode. And this is the output capacitor, which is to reduce the ripple. And this is your output load. And so asynchronous means a single power switch is used. Here you can see only one switch is used. And so additionally, you can use another switch here, because this D1 diode, it is simply transferring the stored energy of the inductor. Sometimes you can just replace D1 by another MOSFET. So in the diode, there's always voltage drop, 0.7 voltage drop. So when the current is circulating, always there's a power loss. But when you use a MOSFET instead of a diode, so the MOSFET turn on resistance is very low. It's around like 10 milliohms. So you can reduce the power dissipation across this diode if you use another power switch like a MOSFET, right? So, but it add more complexity. So you have to switch both these two MOSFETs based on their switch these square wave pulses. So that needs to handle some dead time. So you can't switch them simultaneously. You have to deal with some dead time between these switches. So it will add more complexity. So if you need to deal with a very simple design, so you can just use a diode. So that will reduce the complexity rather than going with two switches. So asynchronous means it only uses one single MOSFET. But in synchronous buck converter, so you have two switches. So these switches are controlled synchronously. That's why they call synchronous buck converters when you have two switches. But asynchronous means you only have one single switch, and the requirement of other switches is accomplished by using this freewheeling diode. Like in switch capacitor converters, also in buck converters, so you have two operating phases depending on the status of the switch. So once you have this switch is turned on, it is charging phase, so the inductor is charging. once you turn off this one, so it goes to the discharging mode. So I will explain this to operating mode. So the gate pulse of this switch is driven by a gate driver. So you can't directly connect your Arduino or anything to switch this kind of power switches. So you always need to have a gate driver IC connected to this one to get the maximum performance. Right. So this comes with the gate driver. So gate driver is simply a IC like this. So it takes power supply to power up, and so from any like a Arduino or any kind of microcontroller signal can be driven to the gate driver, and the gate driver will then drive this MOSFET, right? So the thing is, like Arduinos and everything like can only provide 40 milliamps of output current, very low. You can simply run the LED, right? But this kind of power switch driving, so you need to have like currents from 1 amp to 4 amps. So that's why like you provide this voltage signal coming from the Arduino, and this will amplify this to the current, like driving large current pulses based on the same frequency. So that's why you need a great driver to drive this one. And to generate this gate drive signal, so you need to have some error amplifier. So you compare this output voltage with your desired voltage. For example, if you take 12 to 5 volt buck converter, so the output is 5 volts. So you have this feedback resistors, your reference voltage is 5 volts. So this is what you want to have at the output. So the output is compared with this error amplifier. If there's an error, I mean, like if the output is 4 volt, so you want 5 volts, so there's a 1 volt error. So that error is compared with this PWM generator, because you can't just plug a voltage signal here. So it should be a square wave. So there's a ramp generator. So the ramp generator compare this error signal, and depending on the error signal, if the error is large, so you have more turn on time, and if the error is low, so it has a very low turn on time. Likewise, it is generating this square wave pulse here. And then the gate driver, so the gate driver will drive this one. So that's the basic internal control circuit of a buck converter. The thing is, like without having a controller, you can't get this output voltage fixed, because depending on when you change the load, so the output voltage change. So this error amplifier catch this error and always try to keep the output voltage as 5 volts. So it's another, even like when you change your input supply, if it is a 12 volt, sometimes it could go to 15 volt, or it can go down to 11 volts, or whatever the changes here. So it will affect the output voltage. So the error amplifier try to compensate any error and keep the output voltage at desired level. So without having a controller, you can't get a fixed output voltage. That is why we call this as a regulated output power supply. So the output voltage is regulated, so because you have this feedback control system to regulate the output voltage, no matter how you change your load, or no matter how you change your supply voltage, or no matter any temperature fluctuations going on. So it will always keep a fixed output supply. Right. Now this we have these two operating modes. The first one is the charging phase of the inductor. Other one is this discharging phase of the inductor. In the charging phase, so when the transistor Q1 is turned on, so this transistor is turned on, so it just short circuiting its terminal, so it's like acting as a piece of wire. So now you can see this this battery current can now go through this inductor, and some part of the current can go through the capacitor, other current can go to through this load and circulating back here, right? So this is the charging phase, and so we have this switch mode, switch switching node. So it is known as SW. So which is very important when you're designing your controller, because switch node is a very important thing for dealing with the EMI, right? So it's very fast changing voltage point. And so when you just turn on this switch, so it is just short circuit in this terminal. So you can see if this voltage is V in, so switch node voltage becomes V in, because you know the voltage of across a piece of wire is 0. So switch node voltage becomes 0, V in, supply voltage. And the inductor current will go through this path. And the inductor voltage is at this steady state, this voltage becomes output voltage, V out, your desired level. So the inductor is charging to a voltage. So this voltage is V in, this voltage is V out. So the inductor voltage is V in minus V out, right? So this is short circuiting, and V in comes to here, and this is V out. So you have V in minus V out voltage across the inductor. So that is all about the charging phase. So the inductor creating its flux lines like this. So we keep this inductor to charge and creating its flux lines. Voltage is same. So once we are satisfied with the inductor charge density, now this stored energy of the inductor is there. So we can just reuse its stored energy in the discharging mode. In the discharging mode, what you do is just turn off this switch. So it is open circuit, which means there's nothing is connected to the source side. So this side is disconnected. And now, you know, like the inductor is always try to keep its current circulating, no matter, like inductor current cannot be changed instantaneously. So inductor is looking to circulate its current because it cannot stop its current. So it can pass this current through this capacitor as well as this the load. Now the returning current can come through this diode, because it cannot go through here and come, because there's a bridge here, right? So it can't return from here. So only path is returning back from this freewheeling diode. So that will reduce the flux lines of the inductor, and inductor will circulate in the current. And so the stored energy of the inductor is pushed back to the output capacitor and the load. So these are the very two basic operating mode of the buck mode switch mode power supply. Okay, so I have drawn three waveforms. So first one is power switch. So if you want to turn on this MOSFET, so you have to provide a gate voltage. So when the gate voltage is high, the power switch is turned on, so which is the charging phase. And when the gate voltage is 0, the MOSFET is turned off, so this is the discharging phase. In the charging phase, I have shown you the MOSFET is turned on, so it is short circuiting the input to the switch node. So switch node voltage is simply V in. When you turn off the power switch, so the switch node voltage is simply becomes 0, because you can see, like in this case, this diode is acting as a short circuit, which means this, if this is grounding the switch node voltage is simply 0. Or either you can just assume like this is, if this is 0 volt, there should be this one should be minus 0.7 voltage, but assume like it is ideal diode, so which means switch node voltage becomes 0. So this why we can see in here the switch node voltage is 0. And I will introduce you one concept, which is the frequency of switching and this periodic time of switching. So you can decide how fast you switch this inductor. So the frequency is determined based on your design parameters. So if you want to reduce the size of the inductor and this capacitors, you can always increase the frequency, right? So when you increase in the frequency, the size of the components goes down. So which means like if you're designing a buck converter with let's say 100 kilohertz, you need to have very big inductors, which means like your power supply will be like this, right? If you switch to 1 megahertz, you need to have like very big inductor and very big capacitor. So if you switch in 1 megahertz, so you can just reduce it to like this. So it has only very small inductor and a very small capacitor. But additionally, it has more and more EMI, right? So you have to deal with EMI as well when you're switching at high frequency. And this periodic time is this total time duration turn on and turn off. So it is the summation of turn on time. This is T on time. And this is T off time is the turn off time, this period, right? So the periodic time is TS, which is this total time. It is summation of these two. And T is, if you know the switching frequency, you can calculate the TS. TS is this total duration. When we come back to the inductor, so when the inductor is turned on for the charging phase, right, before that, I will show you the duty cycle. What is meant by duty cycle? Duty cycle is the ratio between the turned on time to the this turn periodic time, right? So duty cycle can, if you have 0 turned on time, which means you just turn off the switch all the time, which means your duty cycle is 0. If you turn on the device all this time period, so the duty cycle is 1. But normally we don't go in this extreme conditions, either fully turned off or fully turned on. But we will switch on between these two values, right? The duty cycle can vary from 0 to 1. And if you know this G on time can be calculated from, if you know the duty cycle, T on is D into TS, right? So just multiplying this, so on time is DTS. And off time is 1 upon DTS. So you can substitute this to this equation and get this equation from here, right? So T on is DTS and T off is 1 minus DTS. So you have to remember these parameters because that is the most fundamentals of the switch mode power supplies. Now, for the inductor, so when you turn on the inductor within DTS time period, so the inductor current is ramping up, right? So inductor current is ramping up, and inductor voltage is simply V in minus V out. So in the previous case, I have shown you. So here, so when the inductor is switch on, so switch node voltage becomes power supply voltage, and the output voltage is V out. So the inductor voltage is V in minus V out. So this is that inductor voltage. So the inductor voltage is positive, so it will enabling ramping up its current. And when you turn off the inductor, so the inductor voltage now becomes the output voltage V out, right? So when you turn off, so this voltage is V out, and this voltage is switch node voltage is literally 0 volt. So it is 0 minus V out is minus V out. So the inductor voltage is minus V out. Earlier we had V in minus V out. Now we have minus V out voltage across the inductor. So the negative voltage of the inductor here, minus V out, will push in the inductor current back to the 0, but it never goes to the 0, and immediately in the next cycle it's turning on, so allowing the inductor current to ramping up. So the average load current, you can draw like a line from here to here using the average area. And this average inductor current is equals to the output load current, which is going through that resistor. And so you have this kind of peak-to-peak ripple at the output due to this switching. And so this is the input power source, the battery current. When the device is turned on, so the inductor current, it should be supplied from either this capacitor or from this battery. Assume there's no capacitor, so which means the battery is providing this inductor current, right? That is this current. And so the capacitor current is when the inductor is charging, so the capacitor current increases, and when the inductor discharges, it is decreasing. So we can derive some basic equations for buck converter using the inductor voltage current relationship. So you know that in inductor voltage is V is equals to L di over dt. For small time duration like this kind of situations, we can assuming like this time is as delta t. So L into delta I divided by delta t is the inductor voltage. During the charging phase, the inductor voltage is V in minus V out. So assuming like the inductor charging current is plus IL. So this time duration is dTs, turn on time. And the inductor voltage is V in minus V out. From here, we can get this equation. And the inductor current is ramping from this point to this point. This is plus IL. So that is that can be change of current, right? This change from here to here, that change is given by this equation. The discharging phase also, the inductor voltage is minus V out. The change of the current is this change, right? That is given by this equation. So in power electronics, we know like the inductor, there's a volt-second balance. So whatever the voltage you apply to the inductor for a certain period of time should be equals to the volt-second product of the next switching cycle. Otherwise, the inductor current will, if you're not driving this continuously, the inductor current can ramp up and like that. So it will saturate and the output will be, the regulator will be go out of the control, right? So always you have to remember, you just maintaining the charge balance. So if the volt-second ratios are the same, so in the first cycle we have this inductor voltage is this one and the time is this, and the next cycle we have the inductor voltage is minus V out into the time duration is 1 minus TS. So that will give you the output voltage as V out is equals to D into V in. So if you know your battery voltage or supply voltage, and if you know your duty cycle, this duty cycle, you can calculate what is the output voltage. So as we know, like the duty cycle is from 0 to 1. So the output voltage can be controlled from 0 to supply voltage, right? Which means if you take a buck converter and you want, like say, you have 12 volt supply, right? So by using any duty cycle, you can get the output voltage from 0 to 12 volt. You can design this controller to achieve any voltage from 0 to 12 volt. That's the what it given by this equation, but you have to know which duty cycle you want. So if you want to achieve 5 volts, so there's a specific duty cycle that you should operate your buck converter. So you can calculate that from this equation, and you can, from your Arduino or anything, you can turn on this to that period, and then you can achieve this 5 volt. So I have shown you this output capacitor is placed to reduce the peak-to-peak ripple because this inductive switching will causing some ripple at the output. So the average inductor current will pass through the load and the net charge across the output capacitor is zero. So if the output capacitor get charged over the time, so its voltage is ramping up, so the regulation will be uncontrolled. So in order to make the controller controlled output voltage or fixed output voltage, so the charge balance of the capacitor is also useful. So using the Q is equals to CV equation, we can see like this is the inductor current waveform. In the charging phase, its voltage is V in minus V out. In the discharging phase, its voltage is V out minus V out. So the inductor is charging like that. So the average current is this one, which is go through the load. So we can assume like this additional charge of the inductor is contributing to, this is the capacitor voltage. So this additional charge is contributing to increase the capacitor voltage from here to here. This is the change of the capacitor voltage. So this area of the inductor, so that is inductor current. So this area, we know like this is IL divided by half, and this time period is half of the periodic time. So we can calculate this stored energy of the inductor using this equation. Q is simply this area, that is the area of the triangle. Triangle area is half BH, half into this this pad length is TS divided by 2, and this height is delta IL divided by 2. And that should be, so we know this change of this current IL from here to here is from previous equation, that value. Therefore, we can calculate this the capacitor change, voltage change, by substituting this stored energy of the inductor to the capacitor. From here, then we can calculate this peak-to-peak ripple as a ratio to the output voltage. So that is given by 1/8, 1 minus d due to ratio into the square of the periodic time divided by the inductance into the capacitor. So derivation is not quite important, but keep remember, so you will know this equation, right? If someone gives you a buck converter and asks you determine the peak-to-peak ripple, so if you know this inductance and the output capacitance, and if you know the duty cycle, and if you know the frequency, you should be able to tell this anyone who is asking you what is a peak-to-peak ripple. Using this equation, you should be able to calculate. These kind of things are also provided in data sheets, maybe asked in your examination as well, right? Now there's a condition called boundary between the continuous and discontinuous in conduction. So far I have explained you the buck converter operating at continuous mode, which means the inductor current will never reach a zero. But when you reduce your output load from maximum load to a very small value, so the inductor current will reducing, right? At one stage, it will come to a point, it will fix here, settle here. Before that, I will show you what is discontinuous mode. In continuous mode, you can see here like the inductor current is always having a DC offset, and it will never reaches to zero. So the inductor current is switching like this, right? It will never goes to zero. In discontinuous conduction mode, so the inductor current will starting from zero and goes here, and it will there's a dead time where the inductor doesn't have any energy, right? So that's called the discontinuous mode. The boundary between the continuous and discontinuous mode, so the inductor current in the charging phase, it will starting from 0 to and reach here, and in the discharging mode, it will go back to immediately 0 here. So so the load current condition where the power stage is at the boundary between the continuous and discontinuous mode is where the inductor current falls to 0, and the next switching cycle begins immediately after the current reaches 0. That's what it is explaining here. If the average current falls below ILB, this is the ILB, the boundary current, the circuit moves to the discontinuous mode. So the average current of the inductor, if it go below than this one, so the power supply goes to the discontinuous conduction mode. So this operation is completely go from to a different state. So all the equations we have derived in here is not valid anymore. This equation is valid, but these equations are not valid anymore if you move to the discontinuous mode. So in the boundary, all the equations we have discussed are valid, right? Because it still doesn't go to a dead time. So the boundary current is simply this is the average current, is a half of this because on the average current of this triangle, average area is this boundary current. There's a half of this peak current. So that is given by this equation. And so all you need to do is the maximum boundary current will happen when the duty ratio is at 0.5. In the discontinuous mode, so this is your turn on time, so the inductor current is ramping up. And when you are in the discharge mode, so the inductor current goes down and it will become here. And so there's a period, so the inductor doesn't have any stored energy. So the inductor is just doing nothing here, right? So we call this time period, this is the total time duration. And this is the turn on time, DTS. And this is, we have two terms, delta 1 TS for this turn, this period where the inductor current goes 0, and this is the delta 2 TS, which is this dead time. So basically, this is the microcontroller, the controller turned on the switch, and this total period is turn off period, and it has now two components. One component where the inductor current goes 0, and other components for this dead time. And so using the volt-second ratio, so we know like in the turn on time, the volt-second is the inductor voltage is this one into the DTS. And in this period, so the inductor voltage is minus V out. Delta 1 TS is this time. From here, we can derive this equation using D and delta 1. And IL peak is this one, which is given by this equation. And the output current is this current, the average current. So it can get from getting this total area divided by the total time. And substituting that, we can find this average output current, right? Don't worry about this equation. So these are a little bit complicated, but it is better to have some basic understanding. There's two operating modes, the continuous conduction mode and discontinuous conduction mode. In the continuous conduction mode, so the current is always higher than 0, inductor current is always higher than 0. In the boundary, so it goes to 0 immediately. And in the discontinuous conduction mode, it goes to here and becomes a time, it is called as dead time. So now inductor current is formed. Okay, we will have a short break, and we will starting from the power loss of a buck converter in next coming slides. So we will meet around after 10 minutes break. As we can see here, we have this LM2596 buck converter. So the efficiency goes against the input voltage as well as this output voltage. You could see here when this when it's providing 3 amps load current, when the output voltage is 20 volts, so the converter can run efficiency close to 95%. If the output voltage is 3.3, so from 5 to 40 volts range. So the efficiency of the converter is lower than 75%. So in ideal buck converter, you can achieve 100% efficiency, but in reality, due to these losses of the components, the efficiency is always below than 100%. So that is what you are seeing from here. And the types of losses associated with the switch mode power supplies, that is common for all the switch mode power supply, not only for this buck converter. The three forms are the DC conduction losses, and the AC switching losses, and the control circuit power consumption. That is, any buck converter needs to have this error amplifiers, feedback network, and everything. So it also consumes a little bit of power, but typically it is very small in a well-designed buck converter. So that is, you have seen the quiescent current and shutdown current. So that's in the range of microamps range. So the contribution for control circuit power consumption is very low compared to these other two types. So let's have a look what is the prime the conduction losses are. So that is primarily due to the voltage drop across the transistor Q1 and diode T1 and the parasitic resistance of the inductor. So let's move back to the power MOSFET. This is P1 transistor. So it has this, even though we have assumed it as an ideal switch, it has an internal resistance, which is RDS on, typically in the range of 10 milliohms to 100 milliohms RDS on resistance. So the power loss can be calculated from this equation. You can see when the power switch is turned on, this switch current is increasing up, and when the switch is off, the switch current becomes zero. So this is this average current, which is the load current, which goes through the inductor. And from here, the power loss is the summation of the energy of the charging phase plus the discharging phase divided by the total time period. So we know the power loss in the discharging phase because there's no current flowing through this transistor. Current is zero, so it is zero. In the charging mode, the inductor current will go through this power switch. So average current of the inductor is load current. So I squared RDS is the turn on resistance of the power MOSFET into TDS time duration is this time period, right? I squared R into the time will give you the energy dissipated. And in order to find the power, so you have to divide it by the complete switching period. So that is I squared, I out is squared into RDS into duty ratio is the power loss of across the power MOSFET. So if you want to get a efficient system, you have to always find a suitable power MOSFET which has the lowest RDS on resistance. Typical values you can find is 10 milliohms to 60 milliohms or 100 milliohms. So always better to go with the lowest possible RDS on resistance. And I squared R is the load current, the square of the load current. So which is not, you can't control that in the design. And based on the duty ratio also, your power loss increases, right? And the power loss of the diode is simply output current into turn on voltage drop across the diode into the time period is 1 minus t, because in this period 1 minus t into ts, the diode will conduct. So based on that, if you know this time period, and when we know this energy loss, and in this period, so the power, there's no current through the diode, so that is zero. And using the same principle, we can calculate the power loss of the diode in this equation. So let's take a look at this, the inductor. So even though we assume it as ideal inductor, in practical inductor, it looks like this. So it has this inductive component and DC resistance. You know, like when you take a coil, right? So you can just put a ohms meter and see its what is the resistance. That is this DC ESR, right? Similar to a capacitor, inductor also can be modeled as a ideal inductor and this resistive part. So that resistance, you can simply use a multimeter and just measure that one. That is the DC resistance of the inductor. So every coil, due to its copper loss, there's a resistance, right? And there's also some capacitances between this each and every coil. So added, and we can get the equivalent capacitance. Like if you build a coil like this, right? And so there is a parasitic capacitance between these two segments, like because any coil, so when the charge is passing, there's some kind of capacitance occurring. So that is called as parasitic capacitance. So that will make an equivalent capacitance here, that is in the range of picofarad range, right? Very small value. So, but for the power loss, the contributor is this DCSR. So if you know the average load current, so the power loss of the inductor is I squared into the DCSR of the inductor. So even the inductor is heating up, this power switch is heating up, and the diode is heating up. Together, these three components will add heat and loss to the system. There could be some ESR of the capacitor and ESR of the input and output capacitors, which contribute some sort of power loss, but that is very small. But remember, these three guys are the main contributors for power loss of a buck converter. So I will give you this example, so you can work by yourself. So we have 12 to 3.3 volts, 10 amps max output power supply. So it is using a MOSFET of the ohm resistance is 30 milliohm, and the inductor has a DCSR of 10 milliohm, and the diode forward voltage drop is 0.7. So find the conduction losses at full load. So in that case, conduction losses at full load means these are the conduction losses. So first one is the power loss of the MOSFET. It is, if you know, this is your load current, I squared R into RDS, I squared RDS into D, right? So you know your load current is 10 amp. So you know your DC resistance, and so duty cycle should be calculated. So you know your input is 12 volt and the output is 3.3. So output is V out is equals to dVe. So using this equation, first calculate this because we have to know V out is dVe, which gives you the duty cycle. So V out is 3.3 and V in is 12 volts. So you can calculate the D. And if you know that one, then you can substitute to this equation to get the power loss of the MOSFET. And power loss of the diode is simply, you know the D and you know the output current. So you know the voltage drop of the diodes, that is 0.7. So you can get this P2 value, and P3 value is I squared R D is so I squared is 10 into 10 squared into DCSR is 10 milliohm. So calculate that P1 value first. Note down this example first, and then you can work on that one and type your answers in the chat box so we can compare them. Find the this one first. So note down this one, then I will go back to this slide, previous slide. So as a fourth year student, I'm not doing this calculation, and you have to do by yourself, because now you are just few months before you just passing out, and you should be able to by just looking at these equations and work out this example. Otherwise, there's no point of having 4 years in the university, and if you can't provide a solution for practical scenario, so you are not ready for graduation. So I haven't seen anyone has worked out this on to get the value for the P1, P2, and P3. So if you know the answer, just type one here. So calculate the duty ratio first. It is simply V out divided by V in. V out is 3.3 divided by 12 is your duty ratio. So if you know the duty ratio, then so you can substitute in this two equations, and get this P1 and P2. And P3 is simply I squared is 10 amps. This is 10 amp. And this is 0.7. And duty ratio we know, and RDS MOSFET is 30 milliohm. And this one is 10 milliohm. So by substituting, you can get these values, and yeah. All right. So I know you will have had a basic understanding of calculating this one. So you can work on this example later. as I upload this, all the things. So to find the converter efficiency at full load, so this is the thing, the efficiency we know. So the P out divided by P in. Or we can write like a P out divided by output power divided by input power, and output power, input power is simply the output power plus P loss. So output power is simply 3.3 into 10 amps. And that added to the power loss that you have calculated here, from here. So you can substitute and find this efficiency of the converter, right? Very simple. So now they are asking, what is the converter efficiency if the power diode is replaced by another MOSFET, which means like this asynchronous, someone wants to change this asynchronous buck converter or synchronous buck converter by changing this power diode to another MOSFET to improve the efficiency. So the plan is to use replace this diode from a power MOSFET and make a synchronous buck converter. What would be the improved efficiency? So this the person who wants to change this the buck converter, he wants to increase the efficiency. So he just planning to replace this diode with another power MOSFET to convert this asynchronous buck converter to a synchronous buck converter. And so he is planning to use the same power MOSFET that is using for input switching, right? And so he just want to know what is the improved efficiency. So all you need to do is, now you know you have calculated the power loss of the power loss of this body diode, right? Now it is required to use a power switch here. And so by using this derivative and derivation and find out this power loss of this, derive the power loss here and get the power loss of this the new switch, and then recalculate P2 component and using this equation and find out what is the change of the efficiency, right? So I will give you this as an activity so you can work by yourself. So that will improve your ability to analyze power converters, right? Maybe in the exam, these kind of questions will come. In the exams, I will just give you the data sheets and all these things, so you have to work by yourself. Now we are moving to the other type of loss, which is the switching loss. You know, this is the power switch. And so when the MOSFET is switching in this period, so this is your gate voltage, right? So when you turn on the device, this period you have to provide a gate pulse, and here when you provide 0 voltage, the gate is off. So the gate voltage is not like a straight square type square wave, so it is just like this kind of ramping signal, right? So the amplified version of this one is this. So during this time, so this voltage across this device, when it is fully turned on, so this voltage becomes 0, and when it is off, the voltage goes to the maximum voltage. And the current, when it is turned on, so the current is increasing like this, and when it is switched off, the current goes down there, right? And there's a overlap time period where this voltage of this MOSFET doesn't go suddenly to 0, so it goes down like this, and the current is also ramping up like that. So during this one, so you can see that there's a product of voltage and current, right? So that contributes the energy loss, because there's you can see the voltage and current have the product, because P is equals to VI. So you can see there's a power loss. Here the voltage is 0 and current has some value. So the power switching loss is 0 here, right? But there's a conduction loss, but switching loss is 0. And in here also the voltage is high, but the current is 0, switching loss is 0. But in this period and this period, there's a overlap between the current and voltage, because the MOSFET cannot suddenly change its current and its voltage. So it's gradually changing its current and gradually reducing its voltage. Due to this overlap, there's a power loss. So in order to calculate this power loss, what you can do here is calculate them separately. So you have to calculate this area 1. So this overlap area 1 and overlap area 2, and multiply it by switching frequency, then it will give you the switching losses. Switching loss is a significant contributor in power converters. So based on that, you have to design your heat sinks and everything. So for example, I have done a similar example in when discussing the MOSFETs. So here also, if you want to find area 1, just get the average of these two voltages. So this average voltage here is VDS divided by 2. Area 1 is VDS. VDS divided by 2 is this this average voltage across here, right? This value, I'm talking about this value. And the average current is this IDS divided by 2. This is that average current. So now we know this average voltage and average current. So if we multiply this by E on time, so that will gives you the total energy dissipated. This area 1 is the total energy dissipated during this E on time. Similarly, you can get the A2 as well. So that is the total energy loss during this period. And now you can substitute here and multiply this by the switching frequency, will give you the power loss of the MOSFET. Right. So the switching loss is also possible due to the inductor core losses. So the inductor, you know, in practical scenarios, so the inductor is built on a core, this kind of ferrite core. It could be any shape or E-type, or it's like a transformer, right? So you can wound your inductor like this. So the flux lines will go like this. But so remember, so if you use a ferrite core or something, definitely due to this hysteresis loss, there's a power loss of the inductor. I'm not going to discuss that in detail, but in practical scenarios, the inductor is heating up due to its DC ESR, as well as to the losses of the core. The core losses is hysteresis loss. If you use an air core inductor, there's no any hysteresis loss. But if you use a ferrite core soft iron, there's always hysteresis loss. Other AC losses are due to this gate driver losses. So you have to provide a gate driver. So the gate driver, if you know the gate drive voltage, this voltage, and if you know this gate charge, so total charge of this capacitances, from the data sheet you can find that, and the switching frequency, based on that, there's a heat dissipation of the gate driver. And also there are some losses due to this body diode. Sometimes it takes some reverse recovery time and like that. So it is also possible to dissipate some heat during this body diode recovery. So all these factors contribute into the final loss of a buck converter. Okay, so today we're going to implement and design and simulate a 5-volt buck converter using LM5085 and using T-down spice simulation. So you have to obtain the input and output voltage waveforms, the inductor voltage, switch node voltage, gate drive voltage, and MOSFET like that. So you also need to obtain the step load response, calculate the power dissipation of the IC, MOSFET, power diode, and everything. And finally, recommend components considering the cost, size and footprint, and additional useful features. And then you have to update because last lecture I have shown you how to select these components. If you select a component, then you can, if it has ESR or any value, for example, if this inductor is 50 microhenry, but it might has a DC ESR of 10 milliohm. So you have to put this equivalent model and just update your model, and you can redo the simulation and see how far it changes from the practical values. So from the market, so if you want to build a buck converter, there are two options for you. The first one is you can buy this IC, which has this power switch inside it, right? So it's a one option. Or you can buy the controller, and which has a separate MOSFET. So you have to buy the MOSFET separately and place it here. So the inductor, output capacitor, input capacitors, everything comes out of this controller. So like I mentioned, so sometimes these MOSFET come inside. So then you don't want to buy the MOSFET or the switch. Sometimes if it doesn't have, so you have to additionally add this on. So the freedom of using external one is you can drive more current and you can manage the heat dissipation. So you have to add these capacitors, diodes based on the recommended values from the datasheet. So before we move into the example, the next one I will explain you the datasheet. So before we move into that, if you have any questions, you can ask. Otherwise, we can just discuss the datasheet and then move into the spice simulation. Okay, now we have this buck converter datasheet, which is LM5085. So it can provide a step-down voltage regulation, so which is useful for automotive infotainment or entertainment systems, battery or supercapacitor chargers, and LED drivers. So this is a typical application example. So we have several pins. So V in and ground is where you provide your power supplies or your battery supply. So you can add input capacitor to provide a short and pulsative current requirement of the device. This RT is used for the time control or time control. I will explain this later. And this VCC is the there's an internal power supply of this power controller. I will explain that also later. And P gate is this one has an internal gate driver, so it is driving this MOSFET. And this is your power diode, and this is the inductor, and this is the feedback resistors for this feedback loop. And you can add some filtering capacitors, and this is your output capacitor. So based on our what we have learned from this lecture, so these are the power devices: inductor, output capacitor, and the diode, and this power switch. These things comes addition. This input capacitor also useful. All the others are provided for additional features, right? So this is a simple method of building a buck converter using an external switch. So this device comes with different footprints. It's always you can select based on your requirement. So this has an internal pad here, which is connected to the ground, which means you can use that for heat dissipation and connect to a ground copper pole. So the pin descriptions are here. RC is for on-time control and shutdown, feedback voltage and the ground. ISN is I sensing current, and the power gate is gate driving signal. VCC is there's an internal power supply of the circuit, and VNC is battery supply. And EP is exposed pad, this one. So absolute maximum rating, so you can't exceed your input source supply beyond 75.6 or lower than -0.3, so then the device will fail. Make sure you are operating between these conditions, your battery supply, and the sensing current and adjustable also should satisfy these requirements. Recommended operating conditions should be like these are the extreme conditions. So if it go beyond that, so the device will fail, no longer you can use. But they are recommending you to operate your input voltage between 4.7 to 4.5 to 7.5, and the junction temperature to -40 to 125. So it has this control circuit current. Operating current is 1.8 milliamps. If it is in the shutdown mode, it is 435 microamps, so very low power loss in the inside control circuit. So these are the efficiency against this load current. So when the load current is high, the efficiency is somewhere here, and light loads is a little bit lower. Likewise, you can observe this datasheet specifications. So the output voltage is always regulated. This shutdown is sometimes if you want to, this power controller, if you want to control it by using an extra Arduino or MCU, microcontroller unit, you can connect that pin to here. So if it is set to 0, the power conversion will be stopped. If it is set to high, the power conversion set to started. Power conversion is started, which means from using an external device, you can control that one, the turn on and turn off of the device. Current limiting is the inductor. So you have to control this current of the inductor. Otherwise, if it exceeds the current of the inductor, maximum current, so inductor will fail. So there are two options here. The first option is either you can use this because current sensing is typically done by using a shunt resistor. So you have known resistor R, and so when the current flows, unknown current flows from this known resistor, there's a voltage generated. If you know this voltage and if you know the R, and you can calculate the current, right? So they are providing two options. The first option is using this internal resistance of the power MOSFET. So in that case, you have to have a wire connected to this pin and another wire connected to here. So then you can find the voltage drop across here. The other option is you can add the additional resistor in series with this power MOSFET, and then connect this to get the voltage across the resistor from these two pins, right? So they are recommending to use this one, because if you want to find this, if you use this internal resistance of this power MOSFET, this one is not fixed value, it is changing with these process parameters. But this one external resistor is more reliable. They are saying this one here. Current limiting operates sensing the voltage across either RDS on of the Q1 or sense resistor. So the current limit function is more accurate and stable over temperature when a sensor resistor is used. So they are recommending us to use a sensor resistor. And the RDS on of a MOSFET has a wide process variation and large temperature coefficients, which means if you use the internal resistance to measure the voltage drop, so this value is widely varying and it is changing with the temperature of the MOSFET. But if you use an external resistor as a current shunt, so it is more accurate. You know, inside, as you can see, there are plenty of devices inside this circuit, right? So even this input voltage can go to 75 volt, but these kind of logic circuits typically want some voltage around like 5 volt to 7.5 volt or something like that, very low voltage, right? So you can't directly take this pin and connect all these op amps and everything to 75 volts, because if you provide 75 volt for logic gate, so it will the last time of using that one, because these devices are rated to operate the logic voltage is around 5 volts. So in order to satisfy, so you have to convert this whatever the input voltage comes here to a fixed voltage to drive this internal circuitry, which means even it is a buck converter, in order to run its internal devices, it has a internal power control. So that power controller generate the voltages required for these devices, right? Otherwise, this 75 volt is too much for internal this logic gates and everything. They have this internal power supply, which is associated with the VCC pin. So these are the MOSFET selection like that. So these are recommended components to generate 5 volt output for whatever the voltage you provide here. It will generate a 5 volt output, and the load current is 5 amp. And you have to make sure you are not driving the load current below 600 milliamps. Otherwise, the buck converter will move to the discontinuous conduction mode. The switching frequency is 300 kilohertz, and the maximum peak-to-peak ripple is 5 millivolt. And they are recommended to use this SI7465 power MOSFET from Vishay as this power switch, right? So based on that, these parameters, these components are calculated and displayed in this data sheet. All these calculation procedures are shown here. You can just refer them. Finally, we have they are providing two options. So either you can, if you want to get a reduced output, you can go with this configuration with having this capacitor, additional capacitor. And if you're worried about your cost, if you want to reduce the cost and the ripple is doesn't a factor, doesn't matter, so you can just remove this capacitor. If you add this capacitor, the peak-to-peak ripple is very low, but it adds a little bit cost. So when you're designing the final PCB, these kind of devices cannot be implemented on breadboard, because if you implement on breadboard, there will be a lot of complications. EMI will be high and the ripple is high, and you can't get the desired. Still, you will get the output voltage, but it is not the most efficient or the most effective method of doing that, right? So that's why you have to always build this switch mode power supply on PCBs. So this is their recommended layout. So you will connect your IC here, and it has a pad which is connected to a copper area, and they are adding some thermal vias to transfer the heat from top layer to the bottom layer, and they have this white copper trace for ground, and this is your the input supply where you connect your plus supply from the battery, and this is where you take your output. So make sure you should put the inductor a little bit away from this the chip, because the inductive whatever the magnetic field created the inductor, if you put the inductor very close to this device, so that has the effect on this magnetic flux can couple to your IC and degrade this performance, right? So always keep your power switch away from your control circuit. Normally this side should be coming from the any controller or microcontroller unit. So this is your control side and this is your power side. Make some distance between them. And also there are some hot loops, so fast current changing areas we have discussed. The first one is the inductor charging mode. This current, the total current from the battery will go through this inductor and the power switch and the capacitor and returning back to here, right? So this is a hot loop which carries large current and pulsative large current. So this area should be minimized if you want to reduce this EMI. Otherwise, if you design your PCB with very long tracks, so you probably end up with very bad EMI design and your EMI testing will fail. And second part is when the inductor is discharging, it is current will go through this path and returning back here. This path also should be maintained very small, right? You can't add long traces. Try to minimize this area. Then need to reduce this EMI concerns. Otherwise, when this fast currents are flowing here, so due to this inductance of these PCB traces, they will act as antennas and generate EMI, right? So that will increase the EMI of your design. So if you reduce the length, in a PCB copper trace can be modeled as inductance and resistance, right? So the longer the trace, the more the inductance. So you have to always reduce this inductance of the PCB traces in this kind of power or the large current carrying fast switching tracks. So we are not building a PCB at this stage. So we are just interested on the simulation. So we can go back to the TINA SPI simulation and build this recommended PCB design, recommended circuit designing, which is shown in this diagram to get the 5 volt. Okay, this is how we're going to build this one in TINA TI simulation. All you need to do is go to the Texas Instrument website and find this model. Then you can import as a macro model and add all these resistors, capacitors based on the recommended design, and add some voltage and okay, we have this TINA model. So all you need to do is go to the Texas Instrument website and download this SPICE library file and go to tools and make a new macro model, and you can get this one. or if they have this GNA TI model, you can just download this one and no need to make a marker model. And at this capacitors and these inductors based on this one. And for this MOSFET, go to the Vichy website and search there and find this component, and you can import it to here. This MOSFET is from the manufacturer Vichy SI7465DP. And when you're building this, in order to import this in the marker model, use this DGS sequence if you're building this, importing as a marker model. And if you have all these components here, so you can add some voltage probes here and there, and for the inductor current measure, I have put a ammeter. So all my circuit is built like that. So I can just go to analysis and transient. I can set the time period, maybe set it to 50 millisecond. And my load current is at 5 ohm, which means like if my output is 5 volts, so I will get 1 amps of output load current. So you can change your resistance and similar for different conditions. So the simulation might take some time to process it, simulate for some time. So once the simulation is done, we can come and see how it goes. So I think this will be enough to do the simulation. And go to view, separate curves. So here you can see the inductor current, output current, the gate drive voltage, output voltage, switch node voltage. This is switch node, and VSD is the drain source voltage of the MOSFET. So I can just zoom it out for a bit. Right. So you can see in the output voltage is fixed at 5 volt, and the output current is nearly 1 amps. So the inductor's current is ramping up down based on the gate voltage. So this is a PMOS. PMOS turned on when the gate voltage is 0. You can see in here when the gate voltage is 0, the switch is turned on, the inductor current ramps up. And when the gate voltage is V in, the MOSFET is off and the inductor current goes down. And this is a continuous conduction mode. The inductor current never reaches to 0. And the switch node voltage, you can see when the inductor is turned on, switch node voltage becomes V in when the inductor is turned on or the switch is turned on, and the switch node voltage goes to nearly minus 0.5 volts because there's a voltage drop across the diode that is 0.5 volts. And yeah, that's all about the simulation. So your output is fixed and you can visualize the inductor current and the voltage across the switch node. And in order to find this the losses, you need to calculate this inductor currents and the diode current. And if you want to find this MOSFET switching loss, all you need to do is you have to know this VDS as well as this IDS current. So add an extra component ammeter here. So then you can find this overlap areas and calculate your power loss of the MOSFET. So you can add the ammeter here and the voltmeter here. So by getting the overlapped current and the voltages, like I mentioned, visualize this voltage waveforms, you can obtain this power loss of the switching loss of the MOSFET, that is the switching losses. Conduction losses, you have to calculate, refer the data sheets and find this internal resistance of this one and the internal resistance of the inductor and like that. But overall, if you want to find the efficiency, all you need to do is, if you know the input voltage and input current, yeah, add the ammeter here. So when you simulate, you know your input voltage and you know your input current, so you can calculate the input power. And from here, you know your output current and output voltage, so you can determine the output power. So the efficiency is simply P out divided by P in. So all the losses happening here and everything will be counted internally. But if you know the output power and input power, you can determine the efficiency of the system, right? So simulation is very simple. You can work by yourself. Even I will upload this one to the LMS, so you can try doing this one. And then you can find the answers for the questions I have provided there. And so the answers for these ones are very simple. So you check your simulation model and run it for some time and get the waveforms. Find the duty ratio. Duty ratio is turned on time divided by the time period, that's switching time. Inductor peak to peak current and output voltage ripple. And you can do this step load response by changing this load current suddenly. And calculate the power dissipation of the MOSFET power diode. You can do that. The power dissipation of the IC is this internal control circuit current. You can refer the data sheet and find that one. So you have to recommend the devices. Go and search in DigiKey these values, the inductors, capacitors, and update your simulation model based on the values that you selected. Even for example, if you find a 50 microhenry inductor from DigiKey, so it might has a DC SR, then you have to update your design simulation with these real values. I mean, you can add the inductor, this one replaced with by like an inductor as well as a resistor. Maybe this might has a 10 milliohm and this has a 15 microhenry. But when selecting the inductor, be careful, like in the DigiKey, they are asking what is the current, right? So if you're designing this one to drive a maximum load current of 1 amp, at least find an inductor that can carry more than that current, like 3 amp. If you wish to operate a 5 amp, get the inductor to a current rating more than that. So if your output current is 5 amps and if you use a 1 amp inductor, then the inductor will fail and it will be damaged. That's really important when finding the inductor. Other than that, all the other components are readily available. So you can just find them in the DigiKey site. And if you wish to build something like that, so all you need to do is build a PCB and then import the components and assemble them. So that's all about this lecture. I hope everyone can do the simulation and get familiar with the buck mode switch mode power supplies. And the next week we are going to discuss about the boost converter, which can step up the voltage conversion. So if you have any questions for this lecture, you can ask now. Otherwise, we can end up the session.